used. Okay, why have you not used? Oh my God, so many not used. Okay, so that's something we have to change. Okay, so I will be asking you a lot of questions. I will also give you some homework today. It looks like you need some homework, which is to go and use a quantum computer at the end of today's class. Okay, because everyone has to become hands-on, number one. Number two, I'll also give you another homework, which is an open source homework. We are working with our old systems, therefore did not, what? Okay, fine. So we're going to change all that today. Okay, so I'm going to start sharing here. Oh, okay, allow Webex to share. Oh my God. Okay, maybe I'll drop out for a minute. I will come back. Okay, sorry. Something about my. I have to quit and reopen. Sorry, I'll be back in a minute.
Sure. Okay, sir. We'll wait.
Okay, am I back? Okay, looks like I'm back.
No.
I'm not.
No, sir. Yeah, you have not gone out.
Okay, wait. I have to go out first. Yes.
बंद कर दो, कैमरा बंद कर.
Am I allowed to share?
Yes, sir. Yes, sir. You are allowed to share. Please check.
Okay.
देखो, share. You are a panelist, sir. You can share definitely.
I can. Okay.
Maybe button का पता होगा.
Sir, there is a button below mute.
I know that one, but it's not.
चलिए.
Finally. Okay, it's working.
Yes, sir. You can start. Yeah.
Okay, I think I'm able to share. Okay, excellent. So I hope you're able to hear me, and let's go to the presentation now. So this decade is the quantum decade. Okay, so you're all now beginning your journey into this quantum decade. And in this decade, we are likely to reach what is called quantum advantage. So we are going to discuss all of these things here now in the next, well, 1 hour, 45 minutes. Okay. So we all write programs in a higher level language like C, C++, Java, Python, all of that. Then what happens to that program? That program gets compiled, and that compiler, what the compiler does is it converts this higher level language into machine language. On a classical computer, which is your laptop, your supercomputer, your mobile phone, the higher level language gets compiled into machine language, which is a string of zeros and ones. Okay, so the fundamental unit of computation on your classical computer is zeros and ones. On a quantum computer, this same higher level language, you can program it using Python. Okay, so you can write your programs using Python as you do on your normal computer. The difference is that it gets compiled into qubits. Qubits which have zeros and ones and everything in between. So I suppose you have done all of this in the past few days, where you have understood the principles of quantum mechanics which are used on for programming quantum computers. Okay, so as I said right just now, a quantum computer can be programmed using the same higher level language which you use to program normal computers or classical computers. The difference is that the compiler takes that program and converts it into something that the qubits and the circuits on a quantum computer understand. Okay, so that's what quantum computing is all about. And today we are going to go into a little more detail of how this quantum computer works, what are the problems that you can solve using this quantum computer, and what are some of the applications. How can you get your hands on a quantum computer? How can you program a quantum computer? And how is India positioning itself in the new era of this quantum decade? Okay, this quantum decade where you are one of the early movers. Okay, by taking this course, you have become one of the first people in the world to actually learn about quantum computing. Okay, so that's what today's 1.5 hours or so is going to be about. We are going to discuss exactly this. And remember, if you ask questions, you get an ebook, okay, which will tell you more about where is India headed and how can you contribute to the quantum decade where India hopefully is going to lead. So one question I asked all of you, which was, have you touched, have you used a quantum computer? I saw many people have not used a quantum computer. So one homework for all of you today is, at the end of the day, you have to all go and log into a quantum computer. Okay, so that's number one task for you. Number two is you're going to start your open source journey today. And I hope all of you know Wikipedia is open source, right? All of you can go and I know we all of us use Wikipedia for knowledge, but I don't know how many of you have contributed to Wikipedia. If you have not, today, at the end of the day, you are going to create an account on Wikipedia and you are going to start your open source journey where you are going to write maybe 1 or 2 lines on the quantum computing page of Wikipedia. If you feel you cannot write on the quantum computing page of Wikipedia, and let's say you come from Jaipur, you come from Delhi, maybe just go to the page of Jaipur or Delhi and add 1 or 2 lines about the city which nobody else has written there. Okay. So you're going to do 2 things today. One is start your quantum computing journey. Number 2 is also start your open source journey, which is going to begin by you contributing something to Wikipedia by the end of today. Maybe it's 1 line, maybe it's 1 paragraph, maybe it is, one big article that you're going to write about something you know. Please do that, okay? Because all of us have to become contributors of knowledge. We are all taking knowledge, which is great, but today we are also going to become contributors of knowledge. Okay. So this is, well, it was the most powerful supercomputer in the world at one point. Now it is maybe 7, 8, 9, I don't know what number it is. But this is a supercomputer. Okay, so you all know what a supercomputer is. Supercomputers today are the fastest computers on earth. Okay, the best supercomputer can compute at several, um, computations per second. Okay, per second, whatever x quadrillion, whatever number of zeros that has, that many calculations per second. You all know Moore's law. What does Moore's law say? Moore's law says that every 18 months, compute power doubles. It doubles, okay? Which means that the mobile phone that you own today, 2 years from now, what's going to happen? That mobile phone, the new mobile phone in the market is going to be almost double more powerful, better camera, better gaming, better apps, faster apps, all of those things, right? And that's because of Moore's law, which has been active for several decades. Okay. Now, supercomputers are very powerful, but there are many things that they cannot do. So, can somebody write on chat maybe 2 things which supercomputers today cannot do? Okay, I can't see, so sorry, I don't know what you've written, but I'm going to tell you 2 things, right? Number one, if you try to simulate molecules, this caffeine molecule is one of the small molecules of nature. It's not a big molecule, it's a small molecule. If you were to simulate the caffeine molecule on a supercomputer, you cannot do it today because you need 10 to the power 48 bits to represent the energy configuration of a single caffeine molecule at a single instant, fraction of a second. Okay, to do that you need 10 to the power 48 bits. We don't have a supercomputer that powerful. That's actually 1/10 the number of atoms on earth. Okay, I don't think we're ever going to build a supercomputer that big. And hence, here is one problem: molecular simulation. And remember, caffeine is one of the small molecules of nature. Okay, so hence, molecular simulation is something that quantum computers, well, classical computers can't do, right? Number one. Can quantum computers do? Yes, caffeine molecule can be simulated using 160 qubits. Okay, and we'll understand what is this logical qubits. Okay, what are that? We'll understand, but all you need are 160 qubits to be able to simulate the caffeine molecule. Okay, now to be able to simulate the caffeine molecule, all you need are 160 qubits, as I said. And hence, here is one problem which we think quantum computers can do much, 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 much better than a classical computer, which we know cannot do this molecular simulation. That's one. Number two, we all know what is encryption. Encryption is, for example, your passwords. How are they protected? For example, this Zoom meeting that we are having, even if somebody intercepts the transmission which is happening to your Wi-Fi, they will not be able to listen to this conversation that you and I are able to have, because there is a passcode, and because this transmission, this video that you are receiving is encrypted. Only you and us can view this. Anybody else who does not have the passcode will not get a decrypted version of this video. They will just get a string of zeros and ones, but they won't be able to decode it into this conversation, right? And today, encryption is based on a very simple mathematical basis, which is called prime factorization. What is prime factorization? What are the prime factors of 15? 3 into 5. 3 and 5 are both prime numbers, and they are the prime factors of 15. What are the prime factors of 49? 7 into 7, right? So, so basically today, you take a very large number, a 2048-bit integer, would, if you wanted to prime factorize that large integer, it would take you several billion years on the best supercomputer. Okay, several billion years. Okay, now hence we use prime numbers as our keys today to do this encryption, because we know that the best supercomputers will not be able to decrypt it in reasonable amount of time, and hence we use this. But in the year 1994, Peter Shor showed that using quantum mechanics, if you can actually decode this, you can actually prime factorize on a quantum computer with sufficient number of qubits. Okay, so with a sufficient number of qubits, you can actually do prime factorization on a quantum computer, something which takes billions of years on the best supercomputers can be done within a few hours on a quantum computer. Okay, so this was shown in 1994. This is the year 2025. The algorithm is there. So mathematically, it is shown that you can do exponentially faster factorization on a quantum computer. But we still haven't built that powerful enough quantum computer yet, okay, which can run the Shor's algorithm to decode. So what are countries doing now? Countries are now moving to what is called quantum safe cryptography. Okay, quantum safe is where you don't use prime factorization, you use another method. So basically people are resorting now to lattices to pick numbers out of these lattices to build your keys, and that, at least so far, has been shown to be unbreakable. Well, it hasn't been shown that that is breakable using quantum computers. Okay, so every country is now trying to transition from prime using prime factors or RSA keys. Instead of that RSA encryption, countries are now moving to quantum safe cryptography, because quantum computers are getting more and more and more and more powerful every day, and hence it is expected that in the next few years we will be able to run Shor's algorithm and break today's encryption. Okay, so that's the reason why people are moving to quantum safe. But prime factorization is another example. The first example was molecular simulation. The second example was prime factorization. So these are two examples of problems which we know cannot be done on the best supercomputers today or in the future. And quantum computers can actually solve these problems very, very fast. compared to classical best supercomputers. So, why is this the case? This is because, as I told you, the classical computer, you use the same Java, you use the same Python to do your programming, but it gets compiled into bits, okay? And the bits are not great at modeling molecules. They're not great at doing things like factorization. And that's where quantum computers come in, where the quantum bits or the qubits, which you would have learnt about in the previous classes, has this very beautiful principles it follows called superposition, entanglement, and interference. And these properties enable the quantum computers to build new kinds of algorithms and run them on these quantum computers, which have these properties of superposition and entanglement, which enable them to solve some of these problems exponentially faster. Okay, so that's where quantum computers come in. But are quantum computers going to replace classical computers? No, they're not, because something like multiplication is much, much, much faster on a classical computer. So classical computers are good at many things, and quantum computers are good at many other things, okay? Like factorization, like molecular simulation. So these are problems which the quantum computer is good at, which the classical computer is really, really, really bad at, or cannot even do it. So hence, we are headed to a future where CPU, GPU, and QPU live together. Okay. So today on your laptop, what do you have? You have a CPU. When you run your AI programs, what happens? It goes to a accelerator called a GPU, which is actually, usually it's not sitting on your laptop. It is somewhere in a data center. It's somewhere in the cloud. Okay. The QPUs are out there. So when you run your AI program, for example, that AI program is actually many times running on a QPU in the cloud. Similarly, in future, we expect that the QPUs are also going to be sitting on the cloud. So things like factorization, things like molecular simulation, you will be running them on the QPU. So in future, given a task, you're going to break it up into pieces, saying that, okay, this piece goes to CPU, this piece goes to QPU, and this piece goes to GPU. So that's how the future is going to be. A lot of the computation, of course, will happen locally on your own CPU, on sitting on your laptop. So for example, if you're doing word processing, that's going to happen on your laptop. It's not going to the cloud. It's not going to a GPU. Only when you run your AI programs, they will go to the GPU. And similarly, when you run your quantum programs, they go to the QPU. And this is an era that we are calling this quantum-centric supercomputing, where we are saying that three types of processors are going to work together. And for the first time in history, computing has actually branched. What does that mean? It means there are two types of computers now. One is your mobile phone, your laptop, your supercomputer, which use zeros and ones. Then there is the QPU, which uses qubits to do its computation, and qubits have these special quantum mechanical properties which enable them to do extra special processing on certain tasks like molecular simulation, things like factorization. So I'm going to, stop here for a few minutes and take any questions that people have, okay? So please ask your questions. Okay, so I see this question. Is there something like Moore's law for quantum computers? Indeed, there is. And quantum computers are now currently going faster than Moore's law. Okay, which means that Moore's law every 18 months, the classical compute doubles every 18 months. We pack more and more, transistors in a given square centimeter or space, right? Quantum computers we are seeing is also doubling almost every year right now. So it's also following exponential laws in terms of its growth. Okay. So yes, there is a Moore's law equivalent happening for quantum computers. Can you help me on quantum resistant blockchain? Okay. So quantum resistant blockchain. Wow, blockchain has encryption in it naturally, right? And today it uses the encryption which is available today, things like RSA and others. So in future, blockchain will also need to incorporate in itself quantum safe encryption. Okay, so very simple. There are already quantum safe standards available. They have come out from NIST, National Institute of Standards and Technology, I think, something, yeah. In the US, NIST. Um, so you can actually go to their website. You can see all of that is open source. All the new encryption standards, you can download them and you can actually start playing with them, implement them, and see how they work. Okay, so you can actually build a quantum resistant blockchain using post quantum cryptography, which is quantum safe. Can you please tell how to solve a very, very simple problem? I thought you have done this in the past. All these simple problems in the past 10 days. Okay, so we will come to some of this. Solving a problem, we will come to that. Okay, we will come to how do problems get solved using superposition and entanglement. So any program that you write on a quantum computer, it can be the same thing you are doing on a classical computer. It can be a machine learning problem. It can be an optimization problem. It can be a factorization problem. All of these now need to be rewritten for the quantum computer because you want to exploit factors like superposition and entanglement, which you know are going to give you exponential speed up on certain tasks. So one example I gave you is molecular simulation. Another example I gave you is factorization. So these are problems we know that you can actually solve using a quantum computer. Okay, much faster. So what is the race now? We'll come to what is the race now. For quantum supercomputing with QPU, whether QPU will be on-prem or in cloud. Usually QPUs are on, there are on-prem also, so right now, maybe there are about 100 quantum computers across the world that people have access to, maybe. And usually, for example, I told you today you're going to go and use a quantum computer. You will use it over the cloud. It will not be, of course, sitting on your laptop. From your laptop, you're going to go and access this, QPU, which will be in a cloud in some premises somewhere. So yes, it can be on-prem, but certainly on the cloud, it is accessible today. Which are the good platforms here for quantum coding? So the number one platform that SDK, software development kit, that people use today, about 71% of the world uses a programming language called Qiskit, Qiskit. Qiskit is a Python library, basically. So if you know Python, you can go and start using a quantum computer and start programming it right away. As per Moore's, as devices are exponentially increases, will it power dissipation will be challenging. Yes, of course, power dissipation is a challenge for classical computers, and quantum computers are expected to, you know, reduce your power consumption. Okay, so we will talk a little bit about that also. Can we say prime factorization takes less time compared to classical? Yes, of course, exponentially less time. 8 billion years on a classical computer, 8 hours on a quantum computer. Exponential speed up, okay? But as I said, on certain tasks, not on everything. How will classical be connected to quantum computers? They are already connected. I told you today you can access a quantum computer from your laptop, and that is only possible. Why? Because your computer can be connected over the cloud to a quantum computer. So it is already done. What does cloud QPU mean? Is it like a quantum computer or an actual quantum computer? We're talking about actual quantum computer. That actual quantum computer, just like an actual GPU, is sitting somewhere in a data center. That QPU is what you are going to access. Just like today, most of us don't have a GPU sitting on our laptop. We don't have it. So what do we do? When we run our AI program runs on a GPU, a real GPU, which is sitting on a data center. Same way, a real QPU is sitting somewhere on in a data center. You are going to go and access that. Do you mean edge computing will become order of the day for classical computing? No, I don't think that's what I'm saying. Yes, edge computing with IoT and 5G and 6G and all that is going to become very, very much the norm very soon. But I'm not saying that when I'm bringing in the quantum computer at this point, okay? Edge computing, yes, is becoming more and more and more and more prevalent, and things are going to get speeded up. But edge computer, remember, is your mobile phone. Edge computer, remember, is the sensor sitting in your car. Edge computing, remember, is some of the ACs today, like that AC you see there. Some of them are connected um, to your mobile phone, for example. You can control it. So yes, those are edge devices. They are actually doing some sensing. They're turning on and off and all those things. And they will get smarter and smarter and smarter because AI is going to shrink much more. Okay. So all of that is going to happen. Okay. Quantum and VLSI, can they be linked? Of course. Quantum also is a chip. Anything which is a chip needs VLSI. Okay. People are already into designing, quantum processors and all of those things. So yes, those are very important things. Okay, I think we will. Oh my God, there are so many questions. Okay, we will go back to our conversation now and we will come back. Okay, so we'll come back. And okay, whoever has asked a question, please take my email ID and send an email to me, and I will send you of course, a reply to your question. Plus, I will also send you an ebook which you should read. Okay, all of you. Now, let's move on. Yeah, so sorry, whoever's question I'm not able to answer right now, we will answer them over email. Okay? Yeah. Yeah, sure. Okay, we are back to the presentation. Okay, so as I said, the future is quantum-centric supercomputing where three different kinds of processors are going to work together to solve our problems. Today, two different types of processors are working together, the GPU and the CPU. Very soon, three different types of processors are going to be working with us, right? So an example is, for example, all of you use Chat GPT. So Chat GPT, you ask a question sitting here on your laptop, that question goes to a GPU cluster somewhere in the OpenAI cluster somewhere, processes that and gives you an answer, right? So the GPU is getting accessed through your query that you are giving on question that you are giving on your chat GPT, right? So similar things are going to happen where in future, depending on the task you are giving, it's either going to a GPU or a QPU or a CPU, and you won't be aware where it's going, because right now all you do is use your laptop. All you say is, okay, tell me a little bit about what is how are the weather systems in the world decided, how do they happen. So you write a question like that on chat GPT, it gives you an answer, and you don't care how much of that processing happened on CPU, how much of it happened on GPU. All you care is how is the answer good enough for me. And that's what the future is, where you will just run your tasks and you won't care where that task is running. The orchestration of the task will happen automatically. Automatically it will get decided, something goes to QPU, something goes to GPU, something goes to CPU, and your answer is what you care about, and you will get your answer, right? So that's how the future is. Okay, so now somebody asked me about the um, Moore's law equivalent for quantum computers. I know this is a very difficult slide for you to read. Don't even try to read it. All it is saying is in 2016, there were like 5 qubits. That's it, 5. We in 2024 or 2025 now, we have 156 qubits. 156, 5 to 156. And by 2033 or so, we are going to have about 1 lakh qubits. Okay. So that number is growing exponentially. Okay. It's happening. And also, qubits is just one measure. In addition to qubits, can you write large programs? Is the other measure. And that number has also been growing because the number of gates that can be accommodated or that can be used in the processing or in your program have also been growing in number. Okay. So very, very quickly, the number of gates, the number of qubits, the size of the programs, the size of the problems that you are trying to solve has been growing. Okay, very, very fast. That has been happening extremely, extremely fast. And that's what we meant when we said that, quantum is also growing at the same or faster than the Moore's law at this point of time, right? And there is no expectation that it's going to slow down at any point of time in the near future. So now, I talked about in my, if you remember, my title was, this is the quantum decade, okay? And in this quantum decade, we are going to reach quantum advantage, okay? So what is quantum advantage? I'm sure somebody here knows. Please type on the chat. Okay, we'll start with what is quantum utility. Okay, quantum utility is when we showed that, very good. Somebody said reap benefits tangibly. Excellent. That's an excellent definition for quantum advantage. Okay, so quantum utility is where we showed that, and this happened in 2023, it showed that on certain problems, you can use the quantum computer and you can go beyond the ability of quantum computers simulating that. Okay. So when you are at 20 qubits, 30 qubits, you can, whatever you do on the quantum computer, you can just simulate on a, I'm sorry, yeah, you can just simulate on the classical computer. But once you cross the 60, 70, 80 qubit mark, especially 100 qubits, You have now reached a point where you just cannot simulate on the best supercomputer also. Okay. So quantum utility is being able to say that I am now working with 100 plus qubits, and whatever I'm doing here, sorry, I can't simulate what I'm doing accurately using the best supercomputers. So that's what quantum utility is. And this was reached in the year 2023. Okay. 2023, it was shown that there are now problems which we call utility scale problems, which you can run on the quantum computer, but you cannot simulate well on the classical computer, the best supercomputers. Now, quantum advantage, as somebody said, beautiful word, I now forget, showing tangible usefulness or something. Somebody used excellent words, 3 words they used there. Okay. It is basically saying that I can solve a real life problem, reap benefits tangibly. Excellent. Yes. So I can take a real tangible problem, a real life problem, whether it is in biology, it is in chemistry, it is in finance, it is in optimization, it is in logistics. I can take a problem like that and show that it runs much, 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 much faster on a quantum computer compared to a classical computer. So have we reached quantum advantage? We have not. We have not shown that quantum can do much, 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 much better on a task, a useful task yet. Okay. Yes, Shor's algorithm has shown mathematically that you can do factorization, you can break encryption, but have we run it on a quantum computer yet and shown that it can break, today's, encryption? No, we have not done that yet. So the day we are able to take one business problem or a real science problem or a real technology problem and show that quantum computer does much better compared to classical, because today classical on real tasks always does better than quantum. But quantum is improving, improving, improving. And the day it does better, we are going to be able to say quantum advantage is reached. Okay. When is quantum advantage going to be reached? Type. Somebody make a guess. 2030. Okay. Anandaraman says 2030. When we have classical data into quantum. Well, that we are already doing. What are you talking? Okay. IBM says it will happen in the year 2026, end of 2026 is what IBM has said. There are some startups which have said we are going to reach quantum advantage in the year 2025. Now, the question to you is, who is going to reach quantum advantage first? IBM, somebody says. What is cost in market? As we can see, IBM. Could you please explain about post-quantum? Okay. Sure. So the answer to this question, who is going to reach quantum advantage first? Okay, we are going to get there. We are going to get to the answer to who is going to reach quantum advantage. It's a very, very important question, and we are going to answer that. But I also want to contextualize something at this point of time. Number one, PCs. Who knows which year PCs came? 1999. Okay. PCs came in the 70s. Apple was one of the first to build a desktop mini computer. 1976, who was a competitor to Apple? HCL, India's HCL was a competitor to Apple. It had also built a microcomputer at that time. IBM, of course, the PC came in 1981. Before that, there were already desktop computers from Apple, from HCL also. Okay, pioneers, HCL. Now, but who made PCs useful? Yes, very good. Microsoft did by creating the operating system, the beautiful, simple Windows operating system at that time called DOS. That is how all you, me, all of us, we bought a PC after the operating system made it useful for us. Internet came in the year, World Wide Web came in 1983. Who made World Wide Web useful? Yes, Sun and all these people made internet and World Wide Web. But I think two people made it useful. Number one, as somebody said here, Google. Before Google, there was lots of data on the web, but we didn't know how to find it. Nobody knew how to find it. So nobody used the internet at that time. Second thing, the browser, Netscape. Netscape, before that, we didn't know how to go to websites. No idea how to go to websites. So these two made the internet useful, and they are the ones who made all of us go jump into the internet. Before that, we were all just happy with our own little desktops without internet. We were just happy to use our system for gaming, for this, for that, word processing, everything. We didn't care about internet because internet was something sitting in the lab, wasn't useful. But Google and Netscape made it usable, internet usable. Similarly, AI, who made AI usable? Yeah, so ChatGPT, certainly. ChatGPT, one of them, OpenAI, made sure that all of us are now users of AI. Before ChatGPT, AI was something sitting in a lab. It was used by some people, yes, but not everyone. Now everyone uses AI. Okay. So the system after it reaches, so before OpenAI came out with ChatGPT, Nvidia was a normal company, just a normal tech company. After OpenAI, Nvidia shares rose 900%. 900%, and it became the most valuable company on earth and all of those things. Same Nvidia, same GPUs it used to make before and after OpenAI. There is no change, but the application made the difference. OpenAI brought ChatGPT, and then it opened the eyes to say that, oh, here is GPU. You can now use GPU to do real things like ask questions. Same way, internet was there for a decade. Nobody cared. People started taking note of internet only when they found it useful. Okay. And useful was some applications running on it like Google, like Netscape. Same way, PC was useful only after the OS and all the tools that Microsoft gave us became usable, right? That's what made it useful. So similarly, quantum advantage is about finding that one application which is going to show that quantum computers who have so much potential are now useful. That's what quantum advantage is about. Like somebody said, showing that it is useful on tangible use cases, tangible problems. It's able to do something that you can measure tangibly. Okay. And that's quantum advantage. And I asked you a question, who is going to reach quantum advantage first. Okay. And now we are going to go to some of those answers. Okay. Last year, so I'm going to give you some problems which people have looked at, right? So this is protein structure prediction. We all know last year's physics Nobel Prize was for AI. The founders of AI got the Nobel Prize in physics. Does anybody know the chemistry Nobel Prize? The chemistry Nobel Prize was also for AI. So two Nobel Prizes in the year 2024 were for AI, physics and chemistry. Chemistry one was for protein structure prediction. Okay. Protein structure prediction is basically saying that given these amino acid strings, I know how the protein is going to fold. Is it going to fold like this? Or is it going to fold like this? Is it going to fold like this? Like this? That's what protein structure prediction is. It's saying that given a protein structure, given the string of amino acids that form a protein, the protein shape is going to be like this, it's going to be like this. That shape can be predicted. And why is that shape important? Because that shape determines how you can use that protein to build medicines, to build, amino acids, to build enzymes, to build, many other things in nature are proteins. And if you know how they are shaped, you can then predict how they are going to behave, whether that medicine which is shaped like this can actually go and catch COVID like this. Because a medicine which is shaped like this is not going to go and catch COVID, which is, the spike thing. You remember COVID has that corona appearance. So a protein which is shaped like this, tuck, that's what will catch that. So the protein structure prediction is very, very important problem. And yes, the Nobel Prize in 2024 in chemistry was for protein structure prediction. But we also know that where the sequence similarity is low, we cannot do the protein structure prediction. And that's where quantum computers come in. So here, IIT Madras and IBM together worked on this problem and did solved, well, not, you can't say solved, but they actually showed that you can use quantum computers for predicting the protein structure as one example, right? Similarly, Mustafizur will be talking later this week, I think. So this is a paper written by him where he looked at energy operator landscapes, and this was published in Nature Scientific Reports. Okay, so this is one paper which hopefully he's going to be talking about right later this week when he talks to you. Now I asked you this question, where is quantum advantage going to come from? Okay, who is going to bring it? Now that's a very, very important question, and I want each one of you now to listen very, very carefully. Okay, so India today, many things we are observing is that India today is the talent hub in quantum. We offered a course on NPTEL platform in quantum along with IIT Madras. 15,000 students registered. Out of those 15,000, 7,500 were 12th class students. Okay, 12th class students. There is so much interest here in India, and so many of these children are just going and self-learning. Self-learning, okay. They are going to the IBM platform, just picking up the courses from there, just devouring it, eating it all up, chuck, 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 and done. And so we are observing that India is now one of the biggest users of quantum computers available on the cloud. India is one of the biggest users, okay, of the quantum computers. The number of Qiskit advocates out of India or the certified quantum I forget what they're called, quantum certifications. Okay, the numbers are among the highest from India. The number of downloads or the views out of India on the YouTube channel of Qiskit for learning quantum computing is among the highest in the world. Okay, sometimes it's US, sometimes it's India. That's how it's going. Okay, so this is a McKinsey report which says that India has the highest talent. Okay, European Union, as you know, is many countries put together, and hence as a single country India is where the talent is. Okay, so now given all this talent, where is quantum advantage going to come from? So it has to come from India. It has to come from India. Okay, in the past, PCs, Microsoft, not India. Internet, Google, Netscape, not India. AI, not India. But quantum, we have the talent here, and we better be working on the big problems now to go and solve them. And quantum advantage, we need to make sure that it comes out of India, because this is where the talent is. If talent is not the one that brings out quantum advantage, then I don't know what it should be. Then we're missing the whole point. Why are you taking this course? You're taking this course because you want to learn quantum computing and be the best in the world. If that's not your aim, then you better not be taking this course. Now, India has this national quantum mission run by the Department of Science and Technology. This was announced in the year 2020, and then in 2023 the cabinet approved 6,000 crores for it, and calls were given out. And this year, last year, these calls then got submitted and selected, and right now 17 proposals, so 384 proposals came. Out of that, 17 proposals got selected, and this 42 institutions are now part of the first round of the National Quantum Mission funding. Sorry. Yeah, sorry. Okay, so in the first round, this is, where 43 institutions got funded, and they are going to be leading the initial round of the scientific work that happens in India, right? But remember, this is only the first round. Okay, so for example, MNIT, many of the other institutions, in the next round, you should all become part of it. Your institution should become part of it, because DST does not want this limited to 43 institutions. DST wants this to be a pan-India thing, where all the 9,000 colleges in engineering and other thousands of colleges in sciences also take part in this. Okay, so that's where it becomes a real technology. That's where it starts becoming useful. And that's where, one of you or one of your students is going to come out with those new applications, which is going to bring about quantum advantage, which is going to take quantum technologies out of the lab and into the hands of people to solve real problems. Okay, so that's what this decade is all about, and that's why we are calling it the quantum decade, when we are going to reach quantum advantage, and India as a country is going to start taking the lead. And the whole purpose of the National Quantum Mission is to ensure that India takes the lead. Okay, today there are 34 countries with national quantum missions of their own, more than any other country, more than any other technology. Okay, so every 34 of these countries have national quantum missions. The year 2025 has been declared the year of quantum by the United Nations. The reason is that all these countries believe that if they take the lead in quantum technologies, they are going to have several decades of economic dominance over Earth. And that's the reason why India is saying, let's put this money. And this is just the beginning. This is just the beginning, the 6,000 crores. There'll be more money coming in. The government is saying, let's make sure India becomes the leader in this decade. The quantum mission is started last year. It's going to run until 2030, 2031. And in that period, the goal is to set all the foundation for us to become the leaders in the world in quantum technologies. And why is that important? It is important because it solves some of the tough problems of science, technology, and it gives you economic power, it gives you economic dominance over the rest of the world, right? So that's the reason, okay, that the government is pushing. The other thing is that, and this is what you are all here for, the quantum technology minor program, right? QT01 to QT11. This course organized by MNIT is for QT01. There are 10 more courses, QT01 to QT11. And AICT and DST have announced this, that this year in July semester, colleges, if you can, please start these courses in your colleges. And the aim is that out of the 11 courses, if you offer 6 courses during the 4 years of the students, and any student takes 6 of these courses, then in addition to whatever degree they're earning, BTech in civil, BTech in mechanical, BTech in CS, BTech in electrical, whatever it is, they will also get a minor degree in quantum technologies, okay, which is, you are now telling the people, students, that here, just by taking these 6 courses as part of your undergraduate degree, you also get a second minor degree which is in quantum technologies. Okay, so this is what got announced, and the course that you are taking right now is the QT01, the first course. Okay, so don't worry if you don't know what is a qubit yet, you don't know how to program a quantum computer. All of that MNIT folks and EC, okay, I forget the full form. The goal here is they are here to help you understand these courses, for you to learn and to make sure that you go and teach your students and make India, already a quantum talent hub, into the biggest quantum talent hub in the world. Okay, it's already big. Okay, it's already big, but right now, as I said, there is a race. India, US, sometimes here, sometimes there, but you are going to make sure that through this course, India just gets so much ahead. I don't know how many people saw Dr. Narendra Modi ji's talk yesterday. He gave this example where somebody, from the US, I think, said, when we give a application, when we open a job for yes, that Friedman thing. So Modi ji said, in the somebody in the US told him that when we open a job application, a room gets filled up with applicants, right? And then, but in India, when we do it, a whole stadium gets filled. Okay. So we have the numbers, we have the intelligence, we have the, the interest among our students. I told you 15,000 students registered. Half of them were school students. Nobody told them, please go and take this course. It was all out of self-interest. Okay. All out of self-interest. So there is something happening where kids are today saying, Okay, maybe I'm doing physics, maybe I'm doing CS, maybe I'm doing mechanical, maybe I'm doing civil, but quantum technologies is something very intriguing. It excites me. Teach me a little bit of that. And this is what this course is about. This QT01 that you've been taking for the past few days, the whole goal is here is to enable you to go and start teaching this in the classroom, right? Okay, now I told you today you have to go one assignment number one. All of you have to go and start using a quantum computer. So please just type IBM Quantum. It will take you to this page. You can create an IBM Quantum account. You can go there and start using a real quantum computer right now. Okay, whenever after this class or whenever today, but do it today. At the end of this QT01 course, you should be able to say that I have used a quantum computer. I see Dr. Ashwath is here and he's going to, give you all these technical details about how to do some of these things. Then Mustafizur will also be here with you on Sunday. So it is important for you not only to learn the theory, but also to become hands-on. Okay, it's very important. So I'll stop again for a few minutes and take any questions, right? Okay. I don't know where I am right now in the questions.
Participants, any questions?
I see lots of questions on the
Writing.
Slack. Okay, somebody says IBM Qiskit is expensive. No, sir, it is not expensive. IBM Qiskit is an open source programming language. Okay, it is free. You can also, like I told you today, you are going to write a few lines on Wikipedia. You can also go and start contributing to Qiskit. Okay, it's open source, it's free. You can start contributing to Qiskit, number one. Number two, you can run Qiskit on the quantum computers. I just gave you that link. You just type IBM Quantum, go there and open an account. Everyone gets 10 free minutes per month on the QPO. Okay. So that is more than sufficient for you to get your journey begun. Okay. Get started. So Tarun, IBM Qiskit is not expensive. You can go and start using it for free. You can start contributing to Qiskit for free. Okay. It's open source. And that's why I want each one of you today to go and start with Wikipedia, which is very simple. You can write some words there, go open the quantum computing page and maybe write something there, do that. But it's important for each one of you to start your open source journey, okay? Because the world is moving towards open source. Can you throw some light on various quantum chips, Willow, Majorana, etc., which are in the news, and how are they different? Okay, very good. So I have a ball. Okay, sorry, I have a mobile. I throw this mobile. If I throw it in this direction, what's going to happen? It's going to go in this direction. There is, based on the amount of force, the direction in which I, throw it, I can predict its trajectory and I know where it's going to go and fall. I throw it in this direction, it's going to go and land on that side, right? So this is what classical laws follow, right? You take a ball, throw it, you know where it's going to go, land, where it's going to, what's going to happen to it. Now you take this ball, start shrinking, smaller, 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 into an atom, into an electron, into some molecules, into ions, into small particles. Now what happens? You throw this particle, tuck, and it no longer follows the laws of classical physics. It follows quantum mechanics. The particle, you cannot predict its trajectory. You don't know where it is. It is all over this room, everywhere. Okay. Now, the quantum chip has these small particles, qubits. These particles follow the laws of quantum mechanics, and they are the ones used for computation. So IBM and Google use what is called the superconducting qubits. Okay, yeah, this one, right? This is a fridge here. At the bottom of the fridge, it's close to 0 Kelvin, a few millikelvins. Okay, that's where the processor sits in the IBM one. Okay, that's where the processor sits, and that has the qubits. As you go up, the microwave circuitry, the control systems, all of that, at the top, it is still very cold, 4 kelvins, but much, 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 much less cooler than at the bottom where the processor is. So this fridge is basically your quantum computer. Okay, the IBM and the Google quantum computer, basically. Okay, which at the bottom, that processor is superconducting qubits. And IBM today, the Heron processor has 156 qubits, 156. The Willow processor from Google has 105 qubits, okay, 105. The Microsoft one, it's not yet a computer, okay. In fact, it's not even a qubit yet, okay. So it's very early days for the Majorana processor. They have said certain things that it can scale to millions, it can do a lot of things, but as it stands today, no qubits. Okay, there is no measurable qubit there. Okay, so they have not yet built a quantum computer using that chip which they presented. Okay, they've only shown something and they've said, okay, this will eventually lead to a quantum computer. But all very exciting, very good news. Everybody is on it, working, different technologies. Now, as I said, this is a fridge. This is a fridge, the IBM computer. Are there room temperature quantum computers? Yes, there are room temperature quantum computers also. Light, qubits, single photons can also be qubits. And single photons don't need, refrigeration, right? So people have actually built small quantum computers using light, using photons as the qubits. Okay, so very cold to room temperature, various kinds of qubits are in between there. Different types of qubits like superconducting from IBM, like light from others, and then there are ions, trapped neutral atoms, all kinds of things. Okay, so you can go and look this up. There are at least 7-8 types of qubits which are there. The Microsoft one is called, I think, the topological qubit or something. So there are multiple of them. You should go and look up, and that's one thing. If you learn enough, go and write it on Wikipedia. Okay, please do that. Don't just keep taking knowledge. Start giving, then you learn more. Okay. So that's how the difference is. What can you give clarity on QPU, CPU, and GPU? Okay, CPU, as you know, is your processor sitting on your laptop. String of zeros and ones, it does the processing. GPU is very good at matrix operations. Matrix operations are what are used in your AI. All the back propagation, all those algorithms for AI, all that is a lot of matrix operations, and they are much, much speeded up on the GPU. The QPU, as I told you, is something which enables you to use quantum mechanics laws, things like superposition and entanglement, to solve a certain class of problems like molecular simulation, factorization, and others. Data science use cases which requires performance optimization. Can we migrate the existing process to process by QPU? Yes, you can. You should, in fact, and that's hopefully, you will drive some quantum advantage in this maybe performance optimization problem that you're talking about in data science, right? So yes, there is a race to find some of those problems which can be used on a QPU to solve much faster than you can on a normal, uh, you know, processor, whether it's a CPU or a GPU. Okay, it is said for proper universal quantum computer, we need large number of qubits for error correction to get one correct reading of single qubit. So in many discussions, people argue that the power requirement will outweigh the advantage. As a result, they neglect use universal quantum computer as bogus and myth. What is your take on it? Okay, so error correction. So today's quantum computers are not error corrected. Okay, what does that mean? It means that, you know, mm, the gate operations which I mentioned, you are doing some processing on it. Those things sometimes, for example, you need it to be in this state. And instead of being in that state, the qubit falls into this state because of error. And error can be any sort of error. It can be inherent in the qubit also. It can be inherent in the gate also. All those kind of things contribute to error in your processing. Okay. And so today what we do is we do some error mitigation. What is error mitigation? It is something like, you wear noise cancellation earphones, right? What do you do in that? The noise cancellation earphone, attenuates noise which is present in your surrounding and then amplifies just the signal which is there in the music, for example, right? So similarly, error mitigation is about understanding where the error is coming from and trying to mitigate those things, right? And that's the beginning. Because as this questioner has asked, that error correction actually needs redundancy. It needs you to use certain qubits, extra number of qubits, to then say that, okay, this is the current state of the qubit, right? So, but are so when is error correction expected to happen? So in the IBM roadmap, error correction happens in the year 2029, 4 years from now. Okay. But does it mean that we cannot reach quantum advantage before error correction? No, IBM has said, in fact, 2026 end, we are likely to reach there, right? And if you look at classical computers came in the 40s, right? And error correction only came in 1950. Okay, 1950 is when error correction first time showed up. Hamming showed that error correction is possible using redundancy in the number of bits. Okay, that's what he showed. So nearly for 10 years, there were computers which were not error corrected at all. And you should go and look up the history. These computers without error correction were still useful. They were used in World War II, for example, to break codes. Okay, as one example, right? So quantum computers, similarly, it is expected that even before you reach error correction, you are going to see useful, tangible results come out of it. And, to the people who are saying we should neglect it as bogus and all of that, I think if you are buying into that, then this is not the right place for you. Because the early people who are in some technology have to completely believe it, madly believe it. Okay. You have to believe something like you believe in God, same way you have to believe in quantum. If you are doubting, this is not the place for you. Then you better go to things where there is no doubt for you. Okay. So yes, I'm sure there will be critics. I'm sure maybe they will be right in the end. But The people who are trying to achieve things in quantum cannot have any doubt in their mind. They have to be total believers. They have to believe that I am going to reach quantum advantage. I am going to build that algorithm, because every technology had critics. Okay, people who said, oh yeah, what the heck, it's never going to show up, it's never going to happen. Okay, so everybody, I mean, for every technology there are critics. And yes, there are technologies which completely fail also. So critics are, it's not that they are always wrong, they are right also sometimes, you know. So but if you are somebody who is going to make a difference in quantum, then you better be a believer at this point of time. Maybe when the evidence comes, you can say, okay, sorry, you know, I spent 4 years of my life learning quantum, it was a hoax or it was bogus or whatever it was. But if you want to bring about that change, you can't be a doubter. How many qubits can help a quantum computer solve practical problems in encryption and molecular simulation? So encryption, we know that Shor's algorithm, you require hundreds of thousands of qubits, okay, for the existing Shor's algorithm. But there are now people who are looking at modifications to the Shor's algorithm to say that are there things that Shor missed, which I can now show and reach to some sort of, maybe not in 8 hours, maybe in 80 hours I reach there. But is there a new algorithm I can come up with which I don't have to wait for 10 years to reach that number of qubits, but I can probably show it today using the current number of qubits. And of course, there are always reports. For example, recently there was one out of China which said that they have, you know, come out with a solution. Of course, it wasn't a solution yet. Okay, yes, it was some advancement, right? But I don't think these are things which should stop you, because there are also people, as I said, who believe that they will reach quantum advantage this year, they will reach it next year, and these people are working like mad people trying to reach there. Okay, and maybe they will reach there. Okay, so, and that's why it's important to be a believer. If you are in this, be in it with a full heart. Or if you are a critic, then just go to what you believe in, whether it's AI or whatever it is, right? So I think it's very important to, you know, of course, be critical, but also to have that belief that you're going to make that change in this. I want to work for material simulation and optimization. IBM quantum computers only give 10-minute. How can we improve on that? Yes, so as I said, the IBM quantum computer usage is for 10 minutes free every month, right? Um, Other than that, you know, IIT Madras and LTI Mindtree in India have purchased access to quantum computers where they have more access, lot more access compared to the free 10 minutes. And that problem which I showed you on protein structure prediction done jointly by IIT Madras and IBM is using those systems, right, which they have now access to, right? So yes, in India now there are organizations which have, of course, IBMers also have access. So there are organizations in India which have access, right? I know for a fact that, for example, MAITI also gives out some credits on quantum computers. Okay. So today, you know, if you have certain things that you want to solve, National Quantum Mission is another one where they are looking for, they're soon going to be, I think, coming out with a call for algorithms, I think. Okay, so these are all places where you should be aiming, and congratulations, Kavita, that you have reached a point where you need more than 10 minutes of usage. Okay, because in the world, I'll tell you, there are very few who have reached that point, and whoever has reached that point should be proud of themselves. Okay, and now they should aim higher, much bigger things. Okay, so Kavita, We are expecting you to aim much bigger, look for those problems, and please reach out. Maybe we'll figure out a way for you to uh, use the quantum systems in from other sources, right? So that's one possibility, right? Like GPU can be installed in PCIe or NVLink. What will be the interface for QPU, for superconducting qubit and photon-based qubit? So there are already, I don't know what is this PCIe and NVLink and all these things, but the QPU today is already, there is an interface available for you to access these qubits, to put them into different states, to write programs using these QPUs. So all of that is possible, and more you can start using them. I mean quantum computing and power. Okay. Did I miss some context here? Quantum computing and power. Okay, I don't know. But the thing is, oh, I see. Okay, I found your earlier question. As per Moore's law, devices exponentially increases, power dissipation will be challenging. In quantum, that is not expected to be the case, okay, because you're now solving certain problems exponentially faster, which means your power requirements are also coming down exponentially, right, to solve that problem, right? So as a result, it is expected that you will be able to actually bring down the power requirements as opposed to actually raising those power requirements, because once the quantum computers start solving real problems, quantum advantage, you're actually saying that on certain problems now this quantum computer will be able to solve it much faster, much more efficiently. So already you have reduced the power requirement that was there. Okay, so we'll go back, okay, to the presentation. Okay, we're back. Yes, so now, as I said, homework number 1, all of you have to go and create an account here and start using a quantum computer and reach Kavita's level of just exhausting those 10 minutes and then being able to say that I need more time on a QPU. Okay, so please get to that level. Okay, there's also a platform called IBM Quantum Learning. Okay, so more advanced courses, tutorials, and videos and everything is there where you can go and start your journey. So if you are a beginner, there are beginner courses. If you are intermediate, there are intermediate courses. If you are an expert like Kavita, there are expert level courses also there. Okay, so each one of you can actually find these. And every summer, there is a summer school from IBM, and please participate in that. IBM also helps you conduct what is called the Fall Fest in your colleges. Please, see how you can participate in these the IBM Fall Fest. Okay. In India, last time, I think there were at least 10 colleges across India which had Fall Fests that they conducted, the IBM Fall Fests. So these are all opportunities for you to start your quantum learning journey. Of course, you've all been part of this QT01 course for the past 2 or so weeks, which is great, right? You've all been learning. And now is the time for you to put that learning to use. Go figure out where is other data. Go figure out what can you do, start contributing to Wikipedia, to Qiskit, and all these places, right? So that you find uses for your knowledge and you find hands-on things. You should not just say that, oh, I learned it. After learning, what did you do with it? Did you go and teach the students? Did you go and do a project? Did you go and build something? Did you contribute to some open source code? These should be your goal. Your goal should not only be to be learning, but also to build something out of that learning, because out of that building is what comes out as, contributions, or things like OpenAI, things like Microsoft, things like Google, they're all, somebody saying, okay, I've learned and now I'm going to put that into use. So all of you know Sam Altman, the founder of OpenAI. How many people here know how much he has studied? Okay, nobody. Okay, so he's a third year dropout. Yes, Hina, very good. Third year, dropped out of college. Okay, so you need a big vision. You need to say that I'm going to, whatever knowledge I've gathered, I'm going to now start building something out of it. Okay, you cannot be saying I will do PhD, then only I will do this, or I will do this course, only then I can start building something. Please start building things with the knowledge that you have today. Okay, one thing I missed. Okay, the National Quantum Mission also supports startups. Last year in October or November, they came out with a call. 104 Indian quantum startups applied for funding. Out of that, DST funded 8 startups. Okay, 8 of them. They said, we'll give you money, 8 of these startups. Okay. And now, they're going to come out with another call. The reason is they want young people like you to actually start building things, because that's what is going to lead to our growth as a nation. We need people who are bold, who say that, okay, I've learned and now I'm going to use my learning to build things. Okay. And the government is willing to give you fund. Okay. So it's going to give you funds, money. Somebody asked me for job here, I think. Okay. I just saw flash there. So in my team, I'm hiring BTechs, MTechs, PhDs, everything. What do you need? You need to be the best in programming. You need to be the best in maths, and you need to be the best in physics. 3 things: programming, maths, and physics. The very best. In India, we are seeing that this combination of maths and programming, we are not finding it anywhere in the world. And these are the only people we are hiring. It does not matter whether you have a PhD or a BTech. If you are very good at these things, if you have built programs, if you have contributed to GitHub, if your commits in the past 3 months cross 300 or whatever, 30 or 20 or some reasonable number, we are interested in you. Okay, we don't want people who say I know the theory. Okay, we want people who know the theory and can use that theory to build something. Not only IBM. In India, Fujitsu is hiring, TCS hires, Infosys hires, and LTI Mindtree hires. All of them are hiring on the one side. I showed you these 43 institutions, these things. They are also hiring now. The government has given them money and they are looking for young people who are going to go there and build things in quantum. You need to be able to build things. You cannot just be saying that I know quantum, but I can't build anything. No, then you're not of any use. You need to know quantum and you need to be able to build something, whether it is a physical hardware, whether it is programming, whether it is you need to be an expert at GitHub, you need to go and have contribute to Qiskit, you need to go and write open source code in AI or whatever your preferred thing is. Those are the things which matter. Today, any job you put, there are thousands of applications. Humans don't look at your applications anymore. AI looks at your applications. Okay. So you better stand out. And standing out does not mean only a 9.5 CGPA or whatever. It means having written code in GitHub. It means having built systems which can do something. There is some input and some output coming out of that code which you have written. something where you have written open source contributions. You've said that, okay, in AI, I not only just go and do support vector machines or CNNs or whatever, I also go and build things using these things. Okay. I have built an application for something, maybe connecting my fridge or hacking into my fridge because it's got Bluetooth connection. I know how to hack into my fridge. I know how to go and hack into my car because that's got a Bluetooth connection. I know how to do those things. Or I've built a LLM from my, or at least used an LLM to build a QA system for my college. Or maybe in physics, I put all the books together and built a QA on top of it using the LLMs that are already available. You need to have done projects. You need to have commits in GitHub. If you don't have that, no, you're not needed. Okay, so you better be hands-on and you go and start committing in GitHub. You go, and that's why I said you now need to go and use your learning today to go and start your open source journey. Start with Wikipedia, then move to Qiskit or whatever it is you like, but you need to do open source contributions because otherwise in India, there is no compromise because the best people are sitting here in India. They are self-learning. I told you 15,000 students registered, 7,500 of them 12th class. I put an application out, 12th class students will apply, who know more programming, more physics, more mathematics compared to a PhD. So in India, there is no way if you're not the best, you're going to survive. So you better become the best. Okay. Yes, you can go abroad and find some job somewhere, but in India, you need to be the best because here the best people are already here. Okay, so some use cases, I saw some question there saying, what are the use cases that people have been looking at? So across the world, people are looking in several domains, use cases, so in banking, people are looking at fraud monitoring, portfolio optimization, risk simulation, customer analytics, time series forecasting. In life sciences, I talked about the molecular simulation work, efficient drug research and development, protein folding is one example. Molecular simulation is another which uses some of these things, right? So all of these are examples where people have already started using quantum computers to take these things and for examples, just go Google Scholar is there. You can go there. There are several papers out there in healthcare life sciences. If you're a physics person, high energy physics. If you're a chemistry person, there are use cases in chemistry. If you're a finance person, there are finance use cases. If you are doing machine learning, there are machine learning use cases. And also, what we are finding is that students who are good at quantum are also good at classical. Why? Because the hands-on kids go take a problem for, let's say, from AI, a classification problem, let us say. They take that problem, they try and write a quantum algorithm for it. Okay. And the quantum algorithm, they try and push it further, better. And then they come back to the classical and say, now the quantum is reaching some level. Can I push up the classical? So they push up the classical. So whoever is good at quantum, we are seeing that because of the benchmarking they are doing with classical, they are also the best in classical. Okay. So whoever, if somebody says they are good at quantum AI, they are great at classical AI. We know that. But you need to have done real problems. You cannot say, I read a book, so I'm very good at it. No, you're no good then. You need to have read that book, gone and implemented some real use cases, even if it is on the 10 minutes free, even if it's on some simulator somewhere. And then you need to benchmark it against the best classical results. Okay, so only then you're getting better. Only then you're reaching towards quantum advantage. Otherwise, you're doing toy problems, just keeping yourself happy. Okay, so once, I went to this talk from Rahul Dravid. He said, in cricket, there is that catch thrower. Okay, it throws catches at you, and you can set the level of its difficulty. Okay, you can set it at easy and then catch all the 100 out of 100 catches and say, oh great, I'm very good at catching, I got 100%. Or you can set it at the most difficult level and then you catch only 10 catches and you say that I'm 10% only good at catching today, tomorrow I'm going to become 12. So that's what it is. Don't go after toy problems, go after real problems, go after problems which are going to make a change, which is going to be useful for somebody, and actually build systems. Learning is not about sitting here listening to my lecture or reading a book. It is about whatever you have learned, you have to go and implement it. You got to go and implement it. And today, as I said, two things you're going to do. You're going to go and use a quantum computer. Second thing you're going to do is go to Wikipedia and write something there, maybe on the quantum computing page or any page that you like. Okay, you're going to start your journey of contributing to the world, to building things, to building systems. Pick any of these problems, solve it classically, solve it quantum. You can go to, where are all these data sets available? There are all these places where there are so many data sets available in fraud and many other things. All of these problems, you can go and find them. Go and solve it classically first, and then write a quantum equivalent algorithm to solve it, and then run it on a quantum computer, and then compare. How is the quantum compared to the classical? Try and keep improving. Look for hybrid techniques. Hybrid means quantum plus classical. Can you break up your problem into pieces where something runs on classical, something runs on quantum? You stitch it back together, and your result is much better than what you could do using classical alone or quantum alone. So those are the problems you need to go after. You need to go after the tough problems like Rahul Dravid. You need to go after those tough catches, set the setting to the toughest, and then go do the catching. And that's what Rahul Dravid did. He said he didn't have talent in his team. There were others with talent. VVS Lakshman could just rotate his wrist and tuck, the ball goes. Tendulkar, full of talent. But Dravid, only hard work. You do put the settings to the hardest and go solve them. And that's what you need to do now. Okay, so I will just go over one or two more use cases. So there are things like simulating nature. That's one class of problems quantum computers are good at. Mathematics and processing data with complex structure. Example of that is factorization problem. Another example of that is AI, where data sets, the boundaries are very complex. And that complexity, sometimes, we are observing that quantum computers are able to much better, organize all of that and understand that and give you results there. Okay, for at least small number of features at this point of time, right? As the number of features increases, you need more qubits. So probably we have to wait a bit more, but there are already cases where we are showing that mathematics and processing data with complex structure is much better on a quantum computer. The third one is search and optimization. And there is something called Grover's search algorithm. Please go look at it. 1996, Love Grover, Indian student, well, he was working by then in Bell Labs. He found this thing called the Grover's algorithm for search. Okay, and these are getting applied across industries. This is a smaller list. This one was a bigger list of things that people are already doing using quantum computers and searching for quantum advantage. Okay, so I think we're running out of time. We have 5 minutes. So I'm just going to flash examples that people are working on right now. So Mercedes-Benz, new materials for batteries, for example, new materials for many other things also. Manufacturing uptime, how do you make sure that your assembly line is always up? How do you figure out that there are going to be faults? How do you ensure the supply chain is moving at all times, so that there are no downtimes for your factories, right? So, and gate scheduling, this is an airline problem. You have a limited number of pilots, you have limited number of gates, you have limited number of, you have an aircraft, and those aircraft need to go to Chennai, Mumbai, then Dehradun, all over the place. How do you ensure that the gate scheduling happens in a more effective and efficient kind of a way? So these are all problems where people are looking at. Boeing, one of their biggest problems is corrosion. How do you find new materials that are corrosion resistant? Okay. So these are all things that people are looking at. This is another example from CERN, where they're looking at various kinds of small particles, big particles, image classification. So across the board, people have started looking at multiple kinds of problems, and many of them have started to address this. And as I said, quantum advantage is the next big target that each one of you needs to aim for and get there, right? Get there first. So that's the goal. So I'll stop here because I think we just ran close to time. So we'll take other questions now. What kind of disruptions quantum process possesses to data storage and management? No, nothing in data storage. It is only for processing at this point of time. Okay. Quantum does not do anything. I mean, in fact, it does not store any data. Major applications of quantum computing. Okay, so we just looked at some of those, right? What are those applications we looked at? Where can we learn to simulate quantum secure direct communication protocols? Okay. So communications, there are many tools online which help you simulate. And of course, the simulation is all fine. But I think your goal should be to write a simulator if that's what you want to, because you're all experts and you need to be able to not just use tools which are out there, but you need to actually do these simulations. And you're asking, where can I learn that? I don't know too much about these communication protocols and all, the QKD and all those things, but I'm sure today these kind of resources are available online, and it should not be very hard for you to find them. If you introduce a mechanism to delete qubits, okay, I don't know what that means. How the storage is managed? There is no storage. Everything is in that in time processing. Okay, at this point of time, the number of qubits, the number of gates, you write a program and you run through it once. That's it, gone. After that, the states are lost. There is nothing stored. Can we have general purpose QC if we introduce a mechanism? I don't know what this delete qubit is. Okay, so somebody from physics has to answer you, I guess. Whoever knows this, delete a qubit. What language can be used with QPU? As we use CUDA. Okay, for QPU, I said Python. Python library called Qiskit. Okay, that's a language you can use to program a quantum computer. It's an open source language. You can start using it today. If you know Python, great. And that website I told you, IBM Quantum, in fact, if you don't even know how to program, it allows you to visually create a circuit and solve problems. And very soon, you don't even need to know programming because the coding assistants are already here. They will code for you, but you should not lose your ability to read and write code because coding assistants right now are not that great. Okay. Okay, I don't. Okay, so I see so many questions, and please feel free to send questions. And looking at these questions, I don't know when I'll be able to answer all of these, but great. It's been good talking with all of you. Please go do your 2 homework today, and yeah, and feel free to reach out. I get so many emails, so many LinkedIn and whatever. So please be patient, or keep writing. I'm not going to feel bad if you keep writing and reminding me until I answer. Um, so there was this radio show where they said that most of the world gives up after 3 tries. Okay, but actual conversion only happens after between try number 8 to try number 12. Okay, so keep trying. Try until you get there. Okay, so all the best and thank you so much.
Thank you.
Dr. Rajiv?
Yes, sir. Yes, sir.
Yeah, please.
Thank you, sir.
Okay, Dr. Rajiv, I think your audio is bad, but thank you. I enjoyed speaking to everyone and also seeing so much enthusiasm and so many questions. It's great, I really loved it. And I'm very happy to see all the enthusiasm in all of you coming here, listening to this, sticking around. And please go and spread quantum computing. I think you are the people who are going to now go and teach in colleges, spread everything. And India is really counting on you. Okay, we are counting on you. So thank you so much. Okay, bye.
Thank you, sir.
Thank you so much. Yeah, Rajit, yeah, over to you. Venkat sir, thank you so much for this enlightening talk, and so many things have been clarified. Actually, a lot of things are in different parts and pieces. I think you have tied them up. Actually, I think that's the great job, and because of that, everybody is so much of interaction. Actually, I was sitting through the whole the interaction, and many points were delivered, but at the same time, lot of doubts were clarified, and direction was has now been shown, like you do these, right? So that's the kind of thing, and of course